here. So today we will talk about regression analysis, and I'm going to pull up the PowerPoint slide for regression. Okay. All right. So again, we are extending our discussion of inferential statistics, regression analysis. All along, we have been talking about the relationship. Actually, we have been talking about one variable at a time. Okay, we've been talking about one variable at a time, and let us say we're talking about age. So we look at average age, and we test the hypothesis about average age. Even when we split the sample into 2 or 3, we are still talking about one variable, which is age. When we split the sample into 2, we are comparing two groups that have potentially different average age. Okay, I mean, you're looking at, say, if you come to a workplace, you can ask yourself, what is the average wage of the female and the male staff? What is the average age of the male students at Medgar and the female students at Medgar? What is the average income of people who belong to a union and who do not belong to a union? Okay, you're still talking about their average age or their average wage. Okay, but it's still that single variable, wage. Now, even when we split the sample into 3 and we compare the average wage of Hispanics, African Americans, and Asian Americans, or the average income of 3 or more groups of people, okay? People in the Bronx, people in Brooklyn, and people in New York City, in Manhattan. We're still talking about a single variable, the average age. The average size of houses in Manhattan, in Bronx, in Queens. The average size of house, that is the one variable, okay? And I hope I have really beat that point where we know clearly what we're talking about. Now, the next step in regression analysis, in applied statistics, is where we talk about the relationship between 2 or more variables. Now, we're looking at 2 variables. Let us say we look at wage. But we not only look at wage, we also look at years of experience. So there are 2 variables here, wage, years of experience, all right? We look at the price of a house is a variable. And then the size of the house is another variable, okay? Price, size of the house. Okay, so now we are looking at 2 variables, the price of a house, the size of the house, okay? And so when we go beyond this, and we will go beyond just looking at 2 variables, we're going to look at 3 variables at a time, or 3 or more variables. But let's begin with 2 variables, okay? And so when we are looking at 2 variables, now we're dealing with what in applied statistics we call regression analysis. Sometimes we also use 2 variables to do a correlation analysis. But for this class, I'm going to just focus on regression analysis, okay? And in regression analysis, we are looking at the relationship between 2 variables, okay? One variable is called a dependent variable, and we will call that variable y. And then there is the independent variable that we will call x, okay? And so the values of y depend on the values of x. For example, the price of a house, which is the dependent variable, depends on the size of the house. Okay, and so we can theorize that bigger houses are going to have higher prices. So the price of the house depends on the size of the house. We look at something like wage, and we say the wage that anybody earns will depend on how many years of experience that they have had, okay? And also we can take wage as a dependent variable and say wage depends on the how many years of education, okay? So the two variables, wage and years of education, or we can look at wage and years of experience, okay? So those are, that is an example of our study of relationship between two variables, which we call regression analysis, okay? All right. Now, when we say that the values of the dependent variable depend on the values of the independent variable, right? So what are we trying to look for, okay? What we're trying to look for is we're trying to look for at least three things. One is the nature of the relationship, okay? So if you take two variables and you say, what is the nature of the relationship between those two variables? The nature of the relationship could be a negative relationship, which is to say, as the independent variable changes, the dependent variable will change, but in a negative way. For example, the amount of gasoline in your car, which is the dependent variable, depends on how far you have been driving, the distance you have been driving. And the relationship will be negative. If you fill your car, the tank of your car, what's going to happen is that the more you drive, the less gasoline you will have, okay? So you have a negative relationship. All right. Now, the relationship could be positive, okay? Your wage depends on your years of experience, which is to say, the more years you've been working and experience doing what you are doing, the higher your wage will be, the higher your income will be. That is a positive relationship, okay? Or there could be no relationship. For example, suppose we speculate that your wage will depend on how many brothers and sisters you have. We will find that there's no relationship between the two. So our objective in regression analysis is to determine the nature of the relationship. That is one of the objectives. Then the next thing that we're going to be looking for is the magnitude, the size of the relationship. But the better word is the magnitude of the relationship, okay? To what extent, how much do the values of the independent variable impact on the values of the dependent variable, all right? For example, if we say that your wage depends on how many years of experience, the question you ask yourself, for each additional year of experience, how much does it add to your wage? Maybe every year you get a raise of $50. So for each additional year of experience, your wage will increase by $50. How much does your wage depend on your level of education? How many years of education? So for each year of education in the workplace, you will see that your wage increases by $1,000, so by $700, so by $500. So that's the nature of the relationship. We talk about, say, the price of a house. The price of a house will depend on the size of the house. So for each additional square foot, what is going to be the additional amount that you have to pay for the house for each additional square foot? So we want to know the magnitude of the relationship. Okay? And I'm going to put the alternative word here. Okay, I'm going to say magnitude Okay. The next thing is, how strong is the relationship? How strong? Okay. And that question is answered by asking the more clarifying question: what percentage of changes in the dependent variable is explained by changes in the independent variable? Okay. Going to in the article there. All right. What percentage? It might just be that the price of a house depends on the size of the house, but that may not be the only factor. Okay. So it might just be that the size of the house explains only 10% of the price of a house. But the neighborhood, the number of bedrooms, the facilities, the age, but for now, we are not accounting for that. We're just saying, that price may not be the only factor. There are also random factors that we do not know. And so the size of the house may just explain only 10%. And other variables or random error that we don't know will account for the balance. Okay? All right. So in order to study the relationship, we use what we call the equation of a line. We use the equation of a line. So we have an equation. That equation is specified the way you see there as y is equal to a plus bx. A is a constant value. And I'll use the example of the gasoline. When you fill the tank of your car with gasoline, you start off with 15 gallons. Okay? And so for every mile you drive, for every mile you drive, you lose 1/4 of a gallon. So the relationship B will be a negative number. And so B is the slope or the rate of change. So the rate of change on the gasoline will be, say, a minus B. And minus B could be anything. It could be 1/10 of a gallon. It could be 1/4 of a gallon. But the key thing, it could be 1/20th of a gallon. But B represents the rate of change. And like I say, A is the constant value. A is what you start with. If X is 0, when you fill your tank with gas, then you have not driven any miles. So X will be 0. And so Y will be that initial amount that you put in your tank. All right? The same thing would say when you purchase a vehicle, what is the price of the vehicle? The price of the vehicle is $20,000. But every year, your vehicle loses value as you drive it. The number of miles that you drive the vehicle will cause it to lose value. So in that case, the rate of change, like the number B, which is called the coefficient of the independent variable, that coefficient B will be negative. So every year, your car will lose some value. But the constant value, that is the starting point, when you have not driven the car, when the car is driven 0 miles, will be A, okay? Which will be the $20,000 that you bought the car. So you see some examples here. For example, Y is equal to 10 plus 5x. That's a positive relationship. The constant value is 10, and the rate of change is 5, okay? For example, if X is 3, Y is equals to 10 plus 5 times 3, which is 25. Now, suppose you have another problem where Y is equal to 25 minus 2X. All right? So there you have a negative relationship. If X is 3, then Y is 25 minus 2 times 3, which is 19. So now the next question is, how do we find what B is. That is the 5 and minus 2 that we see there. How do we get to them? Before we get to them, here's an example that I already talked about, okay? So here is the way we specify the relationship we already talked about. Like I said, y is the dependent variable, x is the independent variable, and x is called a predictor variable. Okay. Now, when we specify a regression model, we specify it as y is equal to a plus bx plus e, because we're using statistical data, and the relationships we'll find are not going to be perfect. Okay. So we're going to estimate A and we're going to estimate B. All right. And so when we use X to predict Y, there's going to be an error. The relationship is not going to be exactly perfect. So like we said, how do we find A and how do we find B? We estimate A and we call the estimate of A hat. And we estimate B and we call the estimate of B hat. Now, in order to begin your estimation process, sometimes it's good, let me say always, it's always good to have an idea what the relationship is. So what we do then is to have a graph and we plot the relationships on a graph and have an idea. If you look at the graph that is here, are you able to see it?
Yeah, I can see it.
Okay. So you see the dots there, okay? You see the dots there, and those dots will give you an indication, okay? And they'll give you an indication that this relationship is positive because as X increases, Y is also increasing, so it slopes up. If it's a negative relationship, it will slope down. And here I'm going to give you an example. What I'm going to do, I'm going to try to create what you call a scatter plot, okay? You see the dots here, we call them a scatter diagram. Your assignment that we have for this introduction to regression is mainly a scatter diagram, and I want everybody to do that scatter diagram, and so we can get our feet wet, or our hands wet, whatever, trying to at least have an idea what a regression model does. Do we have a positive or do we have a negative relationship? We want you to at least have an idea, okay? And so I'm going to going to pull up a scatter diagram and illustrate the point, okay? Just give me 1 minute. We're getting there.
Okay.
So I'm going to stop share, and I'm going to share another file. Okay. Okay, do you see the new file?
Yeah, I see it.
All right. So this new file is a file on real estate. Okay. We're going to ask ourselves, a simple question. Now, let the dependent variable here is price. Okay, the price of a house. Okay, and those values are thousands of dollars. Okay, for example, the first house that we see here is 263,000, but we just put to 63.10, and the next house we see here is 182,000. Now, what do you think influences the price of a house? Okay. Now, here we have several variables, but we're going to use only two: the price of the house and another variable. Okay. When we get to the next stage, then we can talk about all these other variables. Think about what influences the price of a house. The price of a house is influenced by the size, for the fact that if you want to make a bigger house, you're going to have to put in more materials and put in more labor. Okay. And so the price of a house is going to depend on the size. Or the price of a house could also depend on the distance from the city. All right. And so that is also possibly a factor. The price of a house could depend on distance from the city. Okay. But we don't know how much it is. I mean, is the price of a house that is far from the city, is it less expensive or is it more expensive? It could depend on the neighborhood and other economic factors. And that's why you have the error in the prediction. Nevertheless, distance from the city center is a significant factor in the price of a house. But we don't know whether the relationship is positive or whether the relationship is negative. And we're going to find out, okay? But think about what could make the difference between, the nature of the relationship between price and distance, all right? Okay, so let's begin with size, okay? So the way you're going to do your assignment is you paint price, and then let us paint size. All right, so we have captured the two variables. Ordinarily, we could do this using the statistical software SPSS, and I'm going to find a way to build that SPSS back in this, because in the real world, you're going to be using SPSS or some other statistical software like SAS, Minitab, or what have you. Okay, we need to get back to it. The pandemic has knocked us off track for 2 years now, but that's okay. So you see where you have the scatter, inside scatter? You see it?
Yeah, I see it.
Okay. And so we see that. Remove that. All right. So what do you think? Does that look like a positive relationship or a negative one?
It doesn't look like either one.
Okay. Is it sloping upwards or is it sloping downwards?
Oh, maybe upward?
It looks more like upwards. Okay. So let's see. The minimum, going to take, trying to see if I can make it clearer for you. Okay. So it's more like it's going upwards. Is that correct?
Yeah.
Okay. All right. Is it clearer now?
Yes.
Okay. It's clearer, looking like it's going upwards. So we're looking at a positive relationship between price and size. Okay. And I'm going to see if, okay, it's not. All right. So let's try another variable. Okay, so let's try price and distance. Now, let me just use this opportunity to give you a little bit insight into practical statistical analysis. Okay. Depends on the location, whether the relationship that we're looking at now is going to be positive or negative. Okay. If, for example, you are in a place like New York City where there's a lot of commercial activity, prices of houses that are further from New York City might be lower because inside New York City itself, prices are very, very high. And people might want to live closer to the city because they want to get to work easier. And so houses closer to the city will be more expensive. Okay, so let's see what happens. You insert, you do the scatter. What do you see?
Oh, it's going negative.
Negative. Okay, it's going negative. So what we see is that houses that are further from the city, as you go further away from the city, the price of the houses drop. You get that? Okay. So
Yeah.
a scatter diagram will give you a basic idea of what you are looking at. Okay? Especially if you're looking at two variables. You get it? Okay? You're just looking at two variables, the scatter diagram will give you some basic notion of what you are dealing with. All right. So I just gave you that illustration, and maybe that will be part of what I will post for the class for office hours. So you can look at that. So let me get back then to our PowerPoint slides. Okay, so here I looked at sales calls and the number of calls. If you're a salesperson, the more calls you make, the more likely you're going to sell. Okay, if you call one person, random luck alone, just that person will not want to buy. Okay, but the more people you call, the more likely you are going to sell. Now, in order to estimate, now remember we said we're going to estimate A, because what we do when we have statistical data is to estimate. So we're going to estimate A using, and when we estimate A, we'll call that estimate A hat. And when we estimate B, we'll call that estimate B hat. Okay? These are what the actual values, the population values will be like, but you do not have the population. So you have a sample, and so you can only use the sample to get an estimate of A and B. Okay? X, the values of X are given as you saw in that last data set. You have the X values, you have the Y values. The Y values being the price of the house, the X values being the distance from the city or the size of the house. And so you have a slope in each case, and that slope is B, okay? Now, for example, if you were looking at, say, the distance from the city, a house in the city center will have a certain amount of price, and so we begin from that. And as we go further away from the city, the prices of houses begin to fall, okay? Okay, so we say we're going to estimate. So how do we estimate that? Okay, we specify the equation. So we have B hat is the sum of X minus X bar times Y minus Y bar divided by the sum of X minus X bar squared. So how do you get those numbers? Okay, are those magical numbers? No, they are not magical numbers. So I'm going to see if I can walk through one of them. So see, B hat is the summation of x minus x bar times y minus y bar. So in order to be able to get B hat, you must find x bar, you must find y bar, okay? So, and A hat is y bar minus B hat times x bar. And so, like I said, you have to find y bar and you have to find x bar. Those are two things that just you need, x bar and y bar. So let's see what that gives us. Well, these are the values we have here, but let's walk through one of them. And I'm going to write down the formula and show you. I'm not going to really have you go through those tedious calculations. Nevertheless, I'm going to have you apply the formula the way they are here. Okay, I'm going to have you apply that formula. I'm just trying to illustrate to you that this is a practical thing, and you can do it. Okay, you can do it. In our days, when we did regression analysis, we didn't have Windows. Okay, we didn't have Windows. We did this almost entirely by hand. I mean, we were just beginning to get into computers, and we had to write these formulas by ourselves. Okay, that was how many years ago? About 46 years ago. So you guys are living in the golden age, where you have things like SPSS, and you have things like Excel. We didn't have those beautiful things. So we did all of this by our hands. Okay. Let us see. I'm going to all right. So I'm going to illustrate one of them for you just so that you can see what we're talking about. And then next week, I am confident. I pray that I'll be able to get back and illustrate this, move this to the next step, because it's a very useful thing for you to learn. Okay. And so let's ask ourselves, what is the relationship between the price of a house and the size of the house? All right. And so I'm going to stop share this, and I'm going to share the Excel file. Okay. So the dependent variable is y, which is price, and the independent variable is going to be x, which is size. All right. Okay, so let's bear with each other. Okay. And so we calculate y bar, which is average. Okay, so this is average for y bar. Okay. So equals average all right. So the average price of house is 221. We can copy that formula. We'll put it for size. Okay, the average size is 222.2223.81. You can see that the process is easy. Okay, might be tedious, but it's easy. Okay, and so we find y minus y bar and x minus x bar. So here we say y minus yb. I'm going to call y bar yb, which is the average of x, and x minus xb. So xb is x bar, which we illustrated. And then we're going to multiply y minus yb, y minus yb times x minus xb, which is part of our formula. Okay. And then we have x minus xb to the power 2, which is part of our formula. And for a simple linear regression, which is what we're doing, you can see the process is very simple. And so y minus yb is equals A2 minus $A dollar $108. Okay, reversing 108, 108. Very easy. You can see, so you get that, and you drag it down. All right. Some values are negative, some values are positive. Okay. And if you do it correctly, right? The answer is 0. If you add the sum, the answer is 0. And so, and the same thing we do here. Minus, okay, we're dealing with C, C2, $C, $108. And so again, we drag down, and we see that if you do it correctly, the sum will be 0. So now the next thing is to multiply j and k. We multiply y minus yb times x minus xb, which is very easy. So equals j2 times k2. Very easy. All right. And see, the sum is not 0 when you multiply the 2. And then we square x minus xb equals k2 to the power 2. All right. You don't have to stretch out the decimals, but since we're using a computer, what's there? So we also get the sum. Now remember the sum, the formula that we had. Okay, so I'm going to write down these sums down. Okay. Summation x minus x bar times y minus y bar is 451, 992.86 And the summation x minus x bar squared is 643,0476.19. And so let's get back to our formula, and I'm going to save this for our purposes. All right, so I wrote down the values we're going to use. So I'm going to stop share and reshare the what we're doing. So you see where we have another problem. So I'm going to illustrate the point here, okay? And I'm going to call this real estate problem. Put a new slide. Okay. Real estate price and size, all right? We're going to use the same formula for our purposes. And y bar, I'm going to write it down as 221.10, and x bar, we're going to write it down as 2223.81. So we write this down. All right, so I'm just going to make things easy for myself, then change the values. Y bar for our problem was 221. Two 1.10 bar was 2223. So we write down the values, and then x minus x bar times y minus y bar was 451,992, 451,992.86, and x minus x bar squared is 643,0476, 643,0476.19. Okay, we didn't get y minus y bar squared. I'm going to get it. So for now, I'm going to take it out from here. Okay. And so we would have 45199. So 643,0474. 643. Sorry. 451,992. 0.86 divided by 643 476.19. And so now that you have those two numbers, could you give me the calculation? What is the result? Do the calculation for me and give me the result.
Okay, 1 second. Four, 5, 1, 9, 2, 6 divided by 6, 4, 2, 4, 6, 4, 7, 0.070289.
All right. Okay, 0.02. What did you get? 0.0702. Is that correct?
Yeah.
Okay. So it's a very long number. So it's going to be 0.07028028. I'm going to say 03. Let's leave it at 4 decimal places. 0.0703. So 02, a lot of numbers. So A hat will be Y bar, which we have as 221.10 minus 0.0702, 0.0703 times X bar, which is 2223.81. So what's the answer? Want to give me an answer? Hello?
Yeah, I'm trying to work it out
Okay,
now.
all right. Okay, so just tell me that. 073, 0703 times 222.81. All right.
I got 64.766157.
Okay. 64.0703 times 222.81 equals times, all right, plus 221.1. And you got 64.76, am I correct?
Yeah.
64.76, very good. So now, once you work these numbers out, you have found A and you have found B. All right, you have estimated A and B. And so the question is, what do these numbers mean? Now, you use these two numbers to get what you call the regression equation, which is that Y is equal to 64.76 and B is a positive number plus 0.0703 times x plus e. There's an error. Now, what is the meaning of that? This regression equation. So let us try to give it meaning. Okay. I'm going to give it meaning. Okay. And then we're going to stop there for the simple reason that we're going to now get into what is the meaning, the regression equation. Okay. So we have the regression equation here, right?
Yeah.
That's going to make it easy. All right, so the regression equation is that. What does it mean? It means that we're looking at the size of the house. So size of the house is the independent variable x, right? So
Yeah.
x, when x is 0, what does it mean for size of the house? If the size of the house, if the value of the independent variable x represents the size of the house, if the size is 0, from your common sense, what does it mean for a house in that location if x is 0? If the value of x is 0, what does it mean? The size of the house is what? Can you think about it?
Yeah, I'm thinking.
If you're trying to look at the values of houses and they said the value of the house is y and depends on the size of the house, x, and x is 0, what does it say about size of the house? What does it say about the house?
You gotta cook the food. You gotta cook the meat.
Then
Well, can I hazard? Can I suggest something?
yeah.
Well, the simple thing means that there is no house there. The house, that's only land, because the house size of the house is 0. Does it make sense?
Yeah.
Means the size of the house is 0, right?
Yes.
Good. When the size of the house is 0, that means there's no house. And so then what would 64.76, the constant, mean? What would it mean to you? If you are looking at urban real estate, A plus B times X. All right. So in this case, B is 0.0703. What will 64.76 represent to you where there is no house?
Isn't it the independent variable
No,
or dependent variable?
no, the dependent variable is Y,
Okay.
which is the value of the house. Is that correct?
Yeah.
It's equal to A when there is no house there.
Yeah, A is the y-intercept, right?
Well, A is the y-intercept. What would it represent to you if you come to a location and there's no house there? What is there?
Nothing.
Something is there. Where do you build a house on?
Mhm.
Where do you build a house on?
You have to make it out of
You build a
wood
house
and
on
bricks and
a piece of what?
pavement.
What do you build a house on? On a piece of what?
You build it from the ground up.
You build a house on a piece of land. Am I
or
correct?
land. Yeah. Mhm.
Very good. So 64.76 thousand would represent what? If Y is the price of the house and there is no house there and the value of X is 0, which means there's no house there, what will 64.76 thousand mean? What will 64,000 mean? The price of what?
The price of the house.
No, the price of the land.
The price of okay.
Because X means the size of the house is 0, means there's no house there, right?
Mm-hmm. Yeah.
And so what is this equation is telling you is that if you come to a location, the basic price of land is about 64,000. And for every square inch of housing, if you build a house, the price of the house would increase by $70. If you multiply 0.076 by 1,000, since the numbers there are in thousands, 0.0703 times 1,000 will give you $70. For each square foot of land, of housing, the price of the house is going to go up by $70. Does it make sense?
Yeah, it makes sense.
Okay. So you are seeing how we use regression analysis, how we use statistical analysis to analyze economic conditions. And here we are analyzing real estate. We can analyze a whole bunch of things. You see the other illustrations here that we have. This is about dividends per share, and we're going to talk about that next time because, okay. And again, we're going to go through it and then use this to explain what we are doing. Here we are talking about sales calls. And so A hat is 19.98. And so ordinarily, if you make no sales calls, now realize when you're doing salesmanship, when you're a salesperson, customers can come spontaneously and buy. And if they come to your desk and you show them something and they buy it, you have made a sale. But it simply says in this equation, okay, simply says in this equation that a salesperson who doesn't make any sales call will sell about $19,000 worth of goods. And for every call they make, on the average, they make an extra $260 worth of sales. That's what it says. If you multiply the number, say, by 1,000, since this represents thousands of dollars. And so basically the equation tells you that a salesperson who doesn't call anybody, who doesn't pick up their phone, is probably going to sell only about $19,000 worth of goods. And for every sales call they make, they should expect and anticipate to make an extra $260 of sales, okay? So the more sales calls you make, the more sales you generate. This is what this equation explains, okay? And so we have all those illustrations here. And so we have this one that we just did. And we also have another illustration where we use regression to explain dividends in finance. For example, the price of a share, okay? Now, it says that the average price of a share is of a share of stock is about $26 in this particular stock. Okay, but when a company pays dividends, for each dollar of dividend that a company pays, the average share will rise by $2.41. That's what this equation here. So this is the equation of the model, okay, or the regression equation, after we make all these calculations. These are all illustrations of the different ways that we can use regression analysis. Here we estimate maintenance expenses of a bus company, okay? And the dependent variable is the cost of maintenance. As you well know, the older a vehicle gets, the more money you spend on maintenance. So we have a model, M is equal to A plus B times H, okay? And A is the fixed cost. Even if you don't drive the vehicle at all, you still got to maintain it, you keep it there. Every month you have to change, every 3 months you have to change the oil, all right? Okay. And the engine gets rusty if you don't use it. So we estimated that. And what did we get? This is the equation of the model. The basic maintenance of a vehicle is $329, and for each additional year that the vehicle is there, you're going to spend about $15.59 to maintain the vehicle. Okay, and so the base cost of maintenance is $394. For each additional year, it will cost an extra $15.59 to maintain the bus. Okay, so we can use this in different ways, in maintenance, in management. And so the next thing then we're going to learn is what we call the coefficient of determination. Since this week, all I want you all to do is to do the scatter diagram, okay, and interpret it. Then next time, we're going to now go into these other, I would say, topics, which is the coefficient of determination and also a test of hypothesis for regression, okay? There has to be a test of hypothesis for regression analysis. All right, and it's all here in our next lecture. And so we're going to go through that, and then I'm gonna try to also run a regression. Okay, I already have a regression model here by SPSS, so that we will focus on being able to interpret an estimation rather than going through the tedious calculation of the estimation. The reason I went through this tedious calculation is to explain to you how those numbers are derived, okay? One of the dangers or one of the disservice that we do to our students is we give them numbers that are easy to calculate, and when they go out in the workplace, they don't even know how the numbers come. And so somebody who knows how the numbers come, even though they may not be in a position or even able to do the crunching, but at least they have an idea where the numbers are coming from, how they are calculated, is very, very useful. So do you have any other questions for me?
No, I don't.
Okay, so try to do the assignments that deal with at least the scatter diagram, so that the next time we're going to go through this again, and we can do the assignments that require you now to actually calculate and test the hypothesis. All right?
Okay.
All right, so have a good night.
Thank you.
Thank
You
you for
too.
stopping by.
Okay. You're welcome. Bye.
Bye.